Hello everyone, welcome back. Now, before we develop our equations for how the properties of our flow change across a shock wave, we're going to go ahead and develop a useful term called the characteristic Mach number. Now, the characteristic Mach number is simply the Mach number based on the speed of sound at the sonic condition. So when the Mach number equals 1. Now, doesn't that mean the Mach number, characteristic Mach number is always 1? The answer to that is no, it's not. But it's based on the speed of sound when the Mach number would be 1. Now, this is really, really helpful, especially in wind tunnels, where I might be, compressing and then expanding my flow to get to particular Mach number in a test section. Or maybe if I'm going through a converging diverging nozzle in a rocket ship. Let's go here. Here's my converging diverging nozzle. And there's my rocket ship going off into space. So in that converging diverging nozzle, what happens is there is a point where the Mach number is equal to 1. I have a point before that where the Mach number is less than 1, Mach number is equal to 1, and then Mach number is more than 1. And so I'm trying to figure out the properties before and after this throat right here. It's useful to use the characteristic Mach number because I can use that to connect things together. If you hear a train in the background, well, there's a train in the background. Okay, let's keep on doing this. So now let's answer a question you might be having. You're saying, well, why isn't the characteristic Mach number 1? Well, it's all because it's based on the speed of sound of that Mach number, not the speed of sound where I am. So here are 3 cases. One case, I'm going sonic. I'm going Mach 1, and then yes, my characteristic Mach number is 1 and my Mach number is 1. It's all good. And just going from the tables, Appendix A, I can go ahead and pull out the temperature versus stagnation temperature ratios for each of these points, for each of these Mach numbers. Now, how do I then find what my characteristic Mach number is for all 3 cases? Well, for the characteristic Mach number, we're going to be saying, more or less that I am going to then be taking my subsonic flow and accelerating it isentropically to Mach 1 and looking at those properties before I calculate this. For a supersonic flow, I'm going to be decelerating it isentropically. And so all in all, my stagnation temperature will stay the same because I'm doing it isentropically, which means it's adiabatic as well. So we're just going to pretend that my temperature right here for this subsonic flow is 300 Kelvin. We'll do that for supersonic as well. And we'll see what happens to that temperature as I go to Mach 1. So to find my characteristic temperature for that characteristic Mach number, I can do that without too much terrible trouble. First off, my stagnation temperature for all these guys is going to be the same, so long as I'm saying that this is the same flow connecting here. Or I'm going from subsonic to this sonic flow and supersonic back to that sonic flow. And so T star is going to be just those ratios. So I have T naught over T sub. I know that one right here. And then I multiply that by my temperature at the subsonic velocity. Those cancel. And I can multiply that by the inverse of this ratio right here, my temperature at the sonic condition. If I wanted to, I could have put a star on this guy to then figure out what T star is. So the T naughts cancel, I'm just left with T star. You'll see things like this a lot where we multiply different ratios together. So, just make sure you're understanding how you do that. I'm just going through, I'm canceling the things that are on the tops and the bottoms until I'm left with just what I'm looking for. So plug that in, what I find is that my characteristic temperature is 274.5 Kelvin for this subsonic flow. The subsonic flow would have to accelerate to get to a Mach 1. When it accelerates, more energy is going into kinetic energy rather than into the internal energy modes, which means that its temperature has to drop. So it cools it down. And if it cools it down, that means that the speed of sound at this sonic condition is actually going to be lower than the speed of sound where I was. And so my characteristic Mach number would actually increase. It would go be a higher value than what I'm at right now. Okay, let's do the same exact thing now for supersonic. So once again, I'm just going to say it's 300 Kelvin. And to find my characteristic temperature, well, it's going to have to slow down. And so I'm going to do the very same thing I did beforehand. I know this ratio, and I want to get just that characteristic temperature, which is right here. So I'm going to multiply it by the temperature at my supersonic condition. That cancels this out. I'm still left with, my stagnation temperature. So I'm going to multiply by the inverse of this ratio to cancel that out. So when I do that, I find that my temperature at reaching that sonic condition would be 334.5. It's actually hotter, so it heats up. So let's go ahead and compare those two now. Okay, so we see that for a subsonic condition, my characteristic temperature, which is going to help me find my characteristic Mach number, is colder. And for a supersonic condition, my characteristic temperature is hotter. And we can already figure out what's going to happen here. So my characteristic speed of sound, right here, the A star, the star is all the characteristic things, is just the gamma R T star. And so I can see something really interesting with this. So if I know my Mach number, in this case it's 0.7, and I'm looking at this and that's equal to, U over A. Okay, this is equal to U over A. And my characteristic Mach number is U over A star. So if I wanted to see how this is going to change, well, I need to realize that how it changes is just going to be A over A star. That's how much it's going to change. That will be the change right here. So let's see here. M star will be equal to U over A times A over A star. That looks good. And so that'd be equal to my original Mach number times A over A star. Okay, and we know what our speed of sound is. It's going to be equal to the Mach number times the square root of gamma RT all over the square root of gamma RT star. These guys cancel, which means it's just going to be based on the ratio of temperatures. I have those temperatures, and so I can already see that for this one, my Mach number, characteristic Mach number, will be higher. And for this one, my characteristic Mach number will be lower. There we go. And once again, while we're not going to be using this all that much to start, we will be using it quite a lot in later chapters where we start talking about converging diverging nozzles, supersonic wind tunnels, where we have this point which is sonic, and we can then connect our properties both before and after that point using these relations. Okay, so that's it for this time. Thank you all for watching. I'll see you later. Bye-bye.